Hi students, so today we'll continue with the discussion of the chapter Electric Charge and Fields. Uh, Today and tomorrow we will be concentrating on MCQs. Okay, so we will be solving the NEET level and JEE level MCQs. And before we solve the MCQs, we should have a revision of all the important formulae which we have covered till now. Okay, so last class I have given you the summary at the end for electric field due to different kind of charge distribution, right? Line charge, ring of charge. Okay, disk of charge I will be doing later. Okay, so don't worry about that. Now here I have covered all the topics which we have done till now. It's a summary. Okay, so it's like a compact version of whatever we have done till now. Okay, so I would like all of you to take a screenshot of this. I hope it is clear. Okay, so the first thing here is quantization of charge. Okay, so any charge should be equal to some integer into E, and E is nothing but charge of an electron in magnitude. Okay, and that is called quantization of charge. If you gain electrons, the charge will be negative. If you lose electrons, the charge will be positive. Okay, so this is plus minus. Okay, and n is integer, so it can be 0 1 2 3 4 0 here means actually it doesn't have charge. Okay, so it's actually is a whole number, right? Then second part says the total charge of isolated system. Isolated means what? The system should not be able to exchange charges with another body. So if the system is isolated, it is not interacting with any other surrounding objects, then the total charge will remain constant. Then if you have 2 point charges at rest, then they will repel each other in the case that the product of the charges is positive. Product of the charges is positive means like charges, plus plus or minus minus. Then the force will be repulsive. It will be along the line joining the charges. If you want to show force on this charge, you have to draw the tail of the vector, right? Whenever you draw a vector like this, if this vector represents the force, the tail of the vector should be at the charge, whichever is experiencing the force. And if the product of the charges is negative, matlab unlike charges, then the force is attractive. Okay, and the magnitude of the force is given by Coulomb's law, 1 by 4 pi epsilon naught q1 q2 by r square, and the value of 1 by 4 pi epsilon naught in SI units is 9 into 10 to the power 9. Okay, suppose the whole space here is filled with some medium, and if they mention the medium, they will also mention the relative permittivity, or sometimes it is called dielectric constant. Whichever word they use, to find the force in medium, you just divide the force in vacuum by the relative permittivity. Okay, so you add one more epsilon r here. Okay, so you divide this by epsilon r. That will give you the force in medium. Then I spoke about electric field at a point. Force is always found on a charge by another charge. Okay, but electric field is always found at a point due to some source charge. So how it is defined? It is force per unit charge, and this is the test charge. Okay, now if you have a charge, source charge is point charge. Okay, then the formula for electric field is 1 by 4 pi epsilon naught source charge divided by distance square. And what is this distance? Distance between source charge and the point where you want electric field. Okay, so basically if you put this force in this formula, one of the charge q naught will cancel, so source charge q will be present. So try to don't get confused between force formula and electric field formula. Force formula will have two charges, and electric field will have only the source charges. Then if you keep here some charge q naught, then the force on that charge will be q naught into E. Okay, because from the definition of E we know it is force per unit charge, matlab force on 1 coulomb. So if you put q naught, force will be q naught into electric field, and this formula is only for point charge. Okay, for line charge and ring of charge we have already seen the So many variety of formulas are there. Okay. Then we spoke about electric field lines. I told you electric field due to a source charge can be represented in the form of lines. Okay. And how to draw the line? Is there any rule? Yes. The tangent at a point on the line. Okay. So if you have a line like this, for example, in this case, then if you want to know the direction of electric field at any point, then what you do? Draw a tangent. That will give you the direction of net electric field. So tangent at a point to the field line gives you the direction of net electric field. If your point charge is positive, electric field will be radially outwards. So it starts with positive charge, and if it is negative charge, it will be radially inwards. If plus charge and minus charge are close to each other, and such a system is called electric dipole, then electric field lines look like this. Okay, they curve like this. Okay, like this, and here it will be just simply straight outwards, right? Because at any point here, due to plus it will be away, due to minus it will be towards. But since plus charge is near, away will be more. So total electric field at any point in this line will be outwards. That's why the field line is straight. And here it will be inwards. And if it is plus plus, not plus minus, then it will be something like this. Okay, we have seen here electric field cannot be there because due to this plus it will be away, due to this plus it will be away. So electric field here will be 0. And if electric field is 0, it means there is not, you cannot draw any tangent. And if you can't draw tangent, then there should be no line also, right? Because if there is a field line, then you can draw tangent. And if you can draw tangent, then it means that tangent shows you the direction of electric field. But we know at this point there is no electric field, so there can't be any line here. Okay, and it will look this way. Then the last point I want to tell you is uniform electric field. Later in the course, you will study what kind of charges produces uniform electric field. Is this uniform electric field? No, because you can see direction is changing. Here electric field is this way. Here electric field is this way. So direction is changing. So how can you call it uniform? Uniform means the magnitude and direction of electric field. Magnitude and direction of electric field should be constant everywhere. So how will you represent uniform electric field? Uniform electric field will be represented by equidistant parallel lines. What lines? Equidistant parallel lines. Why? If it is parallel, then at any point, if you draw tangent, it will be like this. Yes or no? At any point, if you draw tangent, right? So at every point in this space, electric field is this way. Okay. So if this is east, this is also east, this is also east, this is also east, right? So the direction of electric field is uniform. What about magnitude? I told you the properties of electric field lines is such that if the lines are closer, like here, if the lines are closer, electric field in this region is stronger than this region, because here electric field lines are closer. But in this case I want uniform. So I don't want electric field to be stronger or weaker. It should be same everywhere. So the line should not be closer also and farther also. So it should be equidistant parallel lines. Okay. So this kind of lines if you draw with an arrow, then we call such a field uniform electric field. Okay. Fine. Take a screenshot of this and try to time to time revise all the formula. Here one more thing I have forgotten. Sometimes your charges will not be point charge, but it will be continuous charge, like we discussed in the previous video. If you have line charge, okay, then you have to define something called lambda. What is lambda? Linear charge density. Matlab, you take charge in a small part of the wire and divide by the length of the wire. So dq by dl. So that is called your linear charge density. dq is the charge in the small length divided by the small length, which is I have written here dl. You can write dx, dy, whatever you wish. Okay. Unit will be coulomb per meter. Similarly, if the charge is on a surface, like a sheet of charge or a disk of charge, if the charge is on a surface, then we define this quantity whose name is surface charge density, and the letter that we use is sigma. Surface charge density. It is charge on a small area divided by the area. And if the charge is in a volume, right, for example, if you take a solid sphere which is made up of charges, solid sphere made up of charges, then your charge density, this is called your volume charge density. This is linear charge density, surface charge density, volume charge density. What is volume charge density? Take some small volume in that charge, then you divide the charge in that volume divided by the volume. Take that charge and divide by the volume, dq by dv, and unit will be coulomb per meter cube. This will be coulomb per meter square because it is area. Okay, so this covers all the important topics which we have done by now. So now we will be solving MCQs. First we will start with the entrance corner in our EPL, and then we will start doing the transient material. I think the material has been shared with all of you. However, even if you may not have the material, it is not a big issue because I will still be discussing the questions. Okay, I will be discussing the questions before you, before I give the solution. Okay, so let's start. So let's see the first question. So neat. Okay, yeah, this is different. So in what page it is? Tell me the page number. Yeah, it is page number in my material. It is 44. Okay. So entrance corner 2. Entrance corner 2. Not exam corner. Okay. So this E is entrance. Entrance corner 2. Question number 1. Let us see the question. What is the dimension of electric field strength? Electric field. They want dimension. So whenever you want dimension of any quantity, you should know the formula for that quantity. And what is the formula for defining electric field? Force per unit charge, right? So what is the dimension of force? ml t minus 2, mass into acceleration, and charge is current into time. And current's dimension we write a, time is t. So this will be ml, this t will go up, t minus 3 into a minus 1. So that is the dimension of electric field strength, which matches with option D. Let us see the next question now. Question number 2. Charge Q acts as a point charge. So charge capital Q is a point charge, and to create an electric field, its strength measured at a distance of 30 centimeter is 36 Newton per coulomb. So at some distance which is 30 centimeter, they are saying electric field at this point is 36 Newton per coulomb. Okay. Now they are asking what is the magnitude of the electric field strength that you would expect to be measured at a distance of 90 meter. So they want at a distance of 90 meter. R dash 90 centimeter. 90 meter or centimeter? So please convert this meter into centimeter. Okay, you can't give this in centimeter and the other one in meter. Okay, the question will not make too much sense. Okay, so if this is in centimeter, this is in 90 centimeter. So here they want electric field. Okay, so for that you just try to remember electric field is inversely proportional to square of the distance. So the distance was how much before? 30. Now how much it is? 90. That means distance has increased 3 times. So distance has increased 3 times. So if distance in the denominator increases 3 times, electric field will decrease 1 by 3 square, right? 1 by 3 square will be 1 by 9 times. That means the new electric field will be 1/9 of initial electric field. So this way if you do, it is much easier. Okay. So 1 by 9, and what was the initial electric field? 36. So now it is 4 Newton per coulomb. Okay, so 4 Newton per coulomb means option B. Again, they have missed giving you per coulomb in the options. So some few mistakes are there in the UPL. So whenever I'm correcting it, please make the changes. Okay. So the answers are given in Newton, but electric field unit is what? Newton per coulomb. Okay. Let us see the next question now. Question number 3. Consider the electric field lines shown in the diagram below. Options are both A and B are positive, A and B are negative, A is positive, B is negative. So what will be the right answer? For that, you just need to know properties of electric field lines. So if you see the diagram from, from this charge, here is charge A, here is charge B. If you look at the lines, they look like this. I will not draw all the lines, okay? And here it looks like this, right? Here it looks like this. So if you look carefully, lines are coming into A and lines are starting from B. So that means B is positive charge and A is negative charge, right? From the properties of electric field lines. So what is the right answer? B. A is negative, B is positive. So option D. Next question. Observe the electric field lines shown for the charged objects E, F and G. Rank the objects according to which have the greatest magnitude of electric charge beginning with the smallest. So we have kept 3 charges. This is question number 4. E, F and G. Now if you look the lines carefully, here the lines are very much concentrated. Okay, it's very much concentrated. So here lines are very close. Here lines are a little bit far. And here lines are very far. Okay. So wherever lines are very close, you know electric field will be very strong. So near to this charge, if electric field is very strong, then the value of the charge also should be more, because electric field is proportional to source charge divided by distance square. So here if electric field is very strong, how do I know it is very strong? Because lines are very close from the properties of electric field lines, right? So this charge should be largest. So they are asking from the smallest charge. So smallest charge will be this one, right? Because here the lines are very far. So here electric field is very weak. So charge of the source charge will be also very weak. It will be least. So G, then followed by E, then followed by F. So this has the smallest charge, this has the largest charge. And they told you to write from smallest to largest. Option C. Next question, question number 4. Actually, question number 4 cannot be done right now because we have not discussed electric field due to spherical charge till now. Okay, we have discussed for line charge, ring charge. Okay, but we have not discussed electric field due to spherical charge, right? So for question number 4, we will do it later once we find electric field due to spherical charge. Okay. So keep a reminder of this. Okay, I will be remembering. Don't worry. But right now we will not be doing this. We need to know what is electric field due to a spherical charge first. Once we know this, then we can solve question number 4. Question number 5 you can see now. Question number 5 says, how many electrons should be removed from a coin of mass? So there is a coin. So imagine this is a coin. And the mass of the coin is 1.6 gram. So they are asking how many electrons should be removed from this coin so that it may just float in an electric field, and the value of the electric field is given 10 to the power 9 Newton per coulomb. So here this coin has mass and they want the coin to float. Usually you know, if you keep a coin in space, it falls down. But you want this coin to float. Okay. So you know there will always be one force because it has mass. Earth's Earth's gravity will pull this with a force mg. Now if it wants to float here, this force has to be balanced. And there is already electric field in the problem they said. But this coin usually will be neutral. So if you remove electrons from here, if you remove n electrons, which they are asking in the question, if you remove n electrons, then this will have some positive charge plus q. And whenever you keep charge in electric field, it will experience a force. And you know in this question, the force must be in this direction. Must be. And what is the force formula for force on a charge by electric field? Somewhere here I have mentioned, right? So the force on a charge Q, which is kept in an external electric field E, is Q into E. Okay. So for this to float, mg should be equal to QE, right? Net force should be 0. So this force should balance this force. Understood, right? Okay. So what will be Q equal to? Mg divided by E. Now, E is already mentioned. Okay, so can you tell me where should be the direction of electric field? This, you have removed electrons from this coin, right? So the coin has become positive charge, and you know force on any charge kept in electric field is given by this formula. Since you have removed electrons, the test charge which is in the coin, that will be positive. So the direction of force and electric field, if this is positive, these two will have same direction. And you want force in this direction. So electric field should be in this direction. Okay, upward. If it had negative charge, how you can have negative charge? If you give some additional electrons, then in order for force to be up, if this charge is negative, then force and electric field will be in what direction? Opposite direction. So if you want force upward, electric field should be downward. But in this question, it doesn't matter. The force we know upward. So QE, mg should balance QE. Now we need to find number of electrons. We know from quantization of charge, Q is also equal to Ne, equal to mg by E, right? So what will be N? Number of electrons will be mg by E into E, right? What is the mass of the coin? 1.6. Let me rub with all these extra things now. So mass is 1.6 gram, remember. So gram in kg, if you write, it will be 10 to the power minus 3 kg. G value you can write 10 in SI units. E is 1.6 into 10 power minus 19. E value is 10 to the power 9, right? They have given in the question. So these two will cancel. Minus 10 plus 9 will be minus 19 plus 9 will be minus 10. Then minus 10 will go up plus 10, right? So plus 10, then here minus 3, 1, 0, minus 2 will be 8. So N will be 10 to the power 8 electrons. Okay, these calculations you should be able to do yourself. Okay, so how many electrons should be removed from the coin? 10 to the power 8 electrons. Okay, so you can see whichever option it matches, you can tick that one. So the right option is D for the previous question, question number 5. Okay, where we found the charge on the coin. Okay, similar experiment was actually done by Millikan in finding the charge on oil drops, and that is how he found that every charge is equal to integer into E, and E is 1.6 into 10 power minus 19 coulomb. Okay. Sixth question is a very good question. You can put a star mark like this. So what it says, a particle of mass m and charge minus q. So charge on the particle is not plus q, minus q. Enters the region between two charged plates, initially moving along x-axis with speed vx. So vx is the initial speed. Usually in first PU we used to write Ux, but here in the question they have given Vx. The length of the plate is L and a uniform electric field is maintained between the plates. Calculate the vertical deflection of the particle at the far edge of the plate. So basically what the question says is there are two plates, something like this, okay, and in between the plates they have maintained uniform electric field. So uniform electric field, they have not mentioned the direction, so you can take anywhere you want. But you know how, what do you mean by uniform electric field, right? It should be equidistant parallel lines. Here I have told you, right? The lines cannot be closer also, it cannot be farther also, and it cannot be radially outwards. It must be parallel because the direction of electric field should be constant because we are talking about uniform electric field. So let us draw something like this. So these lines represents the uniform electric field. Okay, uniform electric field. Now, this is your x-axis and this is your y-axis in the problem. Now, a charge minus q they have told. This charge is minus q. It enters with a velocity vx, but let us write ux right now. Okay, because we are from first PU knowledge, we know that initial velocity better to write u, right? Later we'll make it v, no problem. So ux along x-axis. So it is moving parallel to x-axis. It has a mass m according to the question. Okay, so the moment this charge will enter the electric field. See, electric field is what, students? It's a region where you feel, where a charge will feel force. So the moment this charge will enter the electric field, it will feel a force. Can you tell me where will be the direction? What is the formula for force on a charge? Q into E. In this problem, the charge is minus. So the force will be opposite to electric field. So electric field I have shown downwards. So force on this particle when it goes inside will be upward. So force will be upward. Okay. So since the force will be upward, the particle will not go straight like this. It will go something like this. It's like, you know, when you throw a chalk straight like this initially, because of a constant force gravity mg downwards, it goes parabola or not. So here also this particle will follow a parabolic path. Okay, what path? Parabolic path. And the path will look something like this. Okay, so once it comes out, then it will go straight. But here it will move in a parabola. Okay. Let me try to show parabola. So once it comes out, it will be straight. So they are asking you, by the time it comes out, what will be its vertical deflection? So it was going like this. Now it has been moved vertically. It has come out by suffering some deflection along y-axis. And this vertical deflection they want. Let us call this y. Okay. So here, by the way, they should have mentioned in the question that gravity should be neglected. So there is no gravity in this problem. Otherwise, there will be one more force mg, right? And if this force will balance this force, it will go straight. Just now we have seen that if the forces are balanced, then the particle, if it was at rest, it will remain at rest. And if it is moving in a straight line, it will continue. Newton's first law, right? Okay. So in this case, they must mention that gravity is neglected. Okay. Okay, so now this particle will go in this parabolic path. Right. Now from here to here, displacement will be this vector, right? From this position, once it enters, then only it will start deflecting. Nah? So once it enters from here to here, this is your displacement vector from here to here. So this is your x component of displacement. This is your y component of displacement. Okay. So if you look carefully now in the question, they have given you the length of the plates also. So if you look carefully, this is your displacement from here to here. Displacement you know, na? From initial position to final position, you draw a vector. So from here to here, this is your displacement vector. So if you take x component of displacement vector, that is your L. So this is nothing but L. Understood? And this y component of displacement is what I have written as y. And that we have to find. Now, the force is, what is the formula for the force in magnitude if I write? Q into E. No need to write minus sign because magnitude I am asking. So if this is the force, what will be the acceleration? Newton's second law. Force by mass. So it will be QE divided by mass. When in first PU the force used to be what? Mg. So if you put here mg, mm will cancel, then acceleration will be what? G. But here it will be QE divided by m, because the force that the particle feels is not gravitational force, it is electrostatic force, which is given by QE formula. Clear or not, students? And I write magnitude because I don't want minus sign in the problem, we only want what is the deflection. Okay. Now this acceleration is along which axis? Look carefully. Where will be acceleration? Wherever is force. If I write vector form, mass is scalar. And where is force? Force is upward along y-axis. So this is your acceleration is completely along y-axis. And if your acceleration, forget about acceleration, if a vector is completely along y-axis, then it means x component is 0. So x component of acceleration is 0, y component of acceleration is this itself. And that is nothing but your QE divided by m. Is it clear? Okay, so we found the x component of acceleration is 0 and we know the y component of acceleration is QE by m. Now let us solve the problem. Now if you look at the formula for acceleration, you found it is constant, right? Q is constant, electric field is uniform, so that is also constant, mass is also constant. So acceleration we found how much? QE divided by m, and this acceleration is along y-axis. Along x-axis there is no acceleration, right? Because the whole acceleration, see the force is along y-axis, right? So acceleration will be also along y-axis, Newton's second law. So now let us, since acceleration vector is constant, we can use kinematics formula. Okay, so Sx, what was the formula? Uxt plus half ax t square, right? Now from here to here, this is the displacement. So what is the x component of displacement? This L, right? So this is your L. Ux is what they called in the question Vx. Let us write Ux only. Time taken from here to here we don't know, t, and this is 0 because ax is 0, right? So this is first equation. Now let us use the same equation for y-axis. So along y-axis if I use sy, what is sy? Uyt plus half ay t square. Now S5 is the y component from here to here. This is displacement. So this is your y component of displacement which they are asking. So this is your y. Uy. Well, initial velocity is completely along x-axis initially, not after some time. After some time, initial velocity will be along the tangent to the path. So your velocity after some time will have both components, Vx also, Vy also. But initially, the particle was coming along x-axis they told. So your Uy will be 0 because initial velocity is along x-axis. And again I am telling you, if a vector is along x-axis, y component of the vector will be 0. Half, what is Ay? Acceleration along y-axis, I have told you already, QE divided by m. And t we can substitute from here. T will be L by ux. So substitute Madi here. So t is L square by ux square. So everything on the right side is given. So this is your answer, right? So which option it matches with? Vertical deflection. Option A. They have written L by Vx whole square. Okay, so you can write this as L by ux whole square. So option. So it's a very good question. Of course, in this question again and again I am telling the mass of the particle sorry, the gravitational force has been neglected, so G has been taken to be 0. But there is electric field, so electric field can also exert force if the particle has charge. Okay. Now let us see the next question, question number 7. This is also a good question. Okay. So question number 7 says a pendulum of mass 40 milligram. Mass of the pendulum is 40 milligram, means 10 power minus 3 gram. Then gram, if you convert in kg, it will be 10 power minus 3 kg. So mass is 4 into 10 to the power minus 610 minus 5 kg. So this is the mass of the bob in the pendulum. Carries a charge. So charge on the pendulum Q is 2 into 10 power minus 8 coulomb. This is the charge on the bob. At rest in a horizontal uniform electric field. So there is a uniform electric field horizontal, 2 into 10 to the power 4 Newton per coulomb. Find the tension in the thread they want and the angle the thread makes with the vertical. G value they are asking you to take 10. That means gravity is present in the problem. So see, they are saying there is a uniform electric field like this. Let us imagine uniform electric field. Okay, horizontal this way. Now in this uniform electric field, if you put a pendulum and if you put charge on the pendulum, then that pendulum will not be in equilibrium in this position. Usually pendulums stay this way in equilibrium. Yes or no? Because mg is balanced by tension. But in this problem, the bob of the pendulum has charge and you are keeping it in electric field. So when a charge is kept in electric field, it will feel a force Q into E. And since the charge is positive in the quotient, force will be this side. So because of this force, the pendulum will not stay in this position. Right? Because another force comes, right? So the pendulum will go somewhere here like this. And according to the question, okay, it comes to rest somewhere and you have to find the angle and the tension. So you have to find the angle that the pendulum makes with the vertical and the tension in the string. And I have told you how to draw tension force, right, along the string away from the body. So there are, what are the forces here? One force will be there, tension. Then here mg will be there. And since electric field is this side and this pendulum has charge plus q will always feel force in the direction of electric field. So electric field is this side, force will be this side. And what is the formula for electrostatic force? Let me write here right now, Fe. Fe means electrostatic force. So it will feel a electrostatic force, okay, QE, but let me give it a symbol as Fe, okay. Now you can see there are three forces acting, one here, and one here. But they told the pendulum is in equilibrium. So net force should be 0. Now if force has to be 0, force is a vector quantity. So if a vector has to be 0, then it means along, see, any vector you can write x component I cap plus y component j cap equal to 0. Okay, so this is what you know from vector study. So if the vector is 0, it means this also should be 0, this also should be 0. If only this is 0, then what will be the vector? Fy. So how this will be 0? You want the whole vector to be 0. So if a vector is 0, x component of the vector and y component of the vector should be 0 separately. So let us call this x-axis and this y-axis. So you can see this force is along x-axis, so it will not have y component. This force is along y-axis, so it will not have x component. But this tension is at some angle, so that tension will have two components, one here if I call this T, then one component here, one component here. Now, if this angle is theta, before you decide which is the cos component and which is the sine component, first you need to know either this angle or this angle. Here they have given this is theta, so this must be also theta. So this is the adjacent side for this tension. So for this triangle, this is the adjacent side. So this component will be T cos theta, and this component will be T sine theta. Understood? So since the bob is in equilibrium at rest, net force along x-axis should be 0. Also, net force along y-axis should be 0. If one of them is not 0, then there will be some net force. So the body will accelerate along either x or either y. But the question said the body is in equilibrium. Now, why will the net force along x be 0? This is my x-axis C. So here one force is there, Fe. Opposite, there is one force, T sine theta. So Fe should balance T sine theta. Or you can say this is positive, this is negative. So Fe minus T sine theta should be 0. So bring minus T sine theta this side. Okay. So the force on the right side should balance the force on the left side. See, this is equation 1, let us say. Then that side, Fy, net force along y-axis. Which are the forces along y-axis? T cos theta and mg. So this mg should be balanced by T cos theta. So mg should be balanced by T cos theta. Equation 2. See, our unknown is what, students? T and theta. So now let us divide equation. This is the angle in equilibrium. In equilibrium, remember later on when I do JEE problems, they may be asking you the maximum deflection. So that maximum deflection is not same as equilibrium deflection. Okay, so all those details I will tell later. So when I say something, listen very carefully. Okay, so let us divide this equation by this equation, because we don't know tension, we don't know angle also. So we cannot use either this equation or this equation. So let us divide. So if you divide, you will get Fe on the left side. Here what is there? Mg. And here T sine theta. On the right side here is T cos theta. So T and T will cancel. Sine by cos theta is what? Tan theta. So tan theta will be Fe by mg. Okay, memorize this result, because many problems will come later where we will use this formula directly. Again, when we can use this formula? When there is a electrostatic force horizontally acting on the charge, and there is the pendulum is in equilibrium. So this is the angle the pendulum makes with the vertical in equilibrium only. So now you can see we can easily calculate the angle. So tan of theta will be equal to, what is the formula for electrostatic force? Don't say 1 by 4 pi epsilon naught q1 q2. That is for 2-point charges. Here where they have mentioned 2-point charges. Here they have mentioned only charge in the pendulum, but they have kept the charge in an electric field. And when you keep charge in electric field, it experiences a force QE magnitude. Okay, so QE divided by mg. Please memorize this result. Okay, Q is how much? 2 into 10 power minus 8. Right? E is 2 into 10 to the power 4. Mass of the pendulum is 4 into 10 power minus 5. Into G value we will take 10. So 2 2s is 4. This is 10 power minus 4. Here also 10 power minus 4. So ratio will be 1. So tan theta is 1. So theta is how much? 45 degree. Right? So once we know tan theta is 45 degree, they also asked you to find tension, right? So theta is 45 degree. Keep a note of this. Now we had a formula where I wrote P mg will balance, mg was down, right? So T cos theta. Remember this formula I wrote, equation 2 I think. You can use equation 1 also. Now what is the mass of the bob? 4 into 10 power minus 5. G is 10. Tension we want. Theta is 45 degree. So if I put 45 degree here, if this is 45 degree, what will be cos 45 degree? 1 by root 2. So tension will be cross multiply 4 root 2 into 10 power minus 4, minus 5 into 10. 10 power minus 5 into 10 will be 10 power minus 4 Newton. So this is the answer for tension. This is the answer for angle. Okay. So option C, right? Yeah. Okay. Let us do one small variation of this problem. Quite interesting, right? Always try to do changes in the question and see what will happen if this change is done like that. So in this question, they told there is electric field like this, uniform electric field, and they kept a pendulum here, right? And three forces will now act: mg, tension, and because of the electric field, QE, and because of this force it will deflect, and finally it comes to equilibrium somewhere here. My question is, if gravity is zero, then what will happen? Where will be gravity zero? Suppose you are inside satellites, where your effective gravity is zero, right? We call this weightlessness in first field. So if G is zero, what will happen? There will be no force mg this side. So no force is this side. So only two forces will be there. Which will be the two forces? Tension and electric Fe, which is Q into E. Right? Mg is not there now. And mg where I made downwards. So tension, how do you do along the string? And QE is this side. So here it cannot be in equilibrium, right? Because there is no mg. And if two vectors should cancel, then they must be in what direction? Opposite. So the pendulum will keep going like this till it will reach this stage. So finally in this stage your QE will balance tension. And that time what angle it will make with vertical? 90 degree. So with vertical it will make 90 degree, and what will be tension? Q into E. You know the value of charge, you know the value of electric field, substitute, get the answer. Okay. So this is how you can easily do this kind of problems. Again students, you must be remembering, you must know vectors very nicely, you must know how to take components of vector, you must know Newton's laws, how to apply. So again and again I am telling, if certain topic you want me to revise, you please let me know in the comment section, so that I will do a separate video for revision of that topic, and you can see that whenever you are free. Okay. Let's see the next question now. Question number 8. So question number 8 says, consider a small test charge located on the electric field line at some point such as P in the figure below. So they have shown you a figure where there is actually a dipole, and you know what kind of electric field dipoles produce, right? I have already drawn like this kind of electric field they produce, right? Okay, and other parts are there. Now there is a point P they have chosen somewhere here. So at that point P they are keeping a small test charge. Here they are putting a small test charge Q now. This is your test charge. The tangent at point P gives which vector they are asking. The tangent at point P. So if you draw a tangent here, that tangent will give you which vector? First option, velocity of the charge. Second, velocity of negative charge. First they said velocity of positive charge kept here. Velocity of negative charge kept here. Acceleration of positive charge kept here. Acceleration of negative charge kept here. Okay, so which one would be the right option? Okay, so you first of all, you go back to the meaning of electric field line. What is electric field line? It is a line which can be straight also, which can be curved also, such that if you draw a tangent at a point, that tangent gives you the direction of what, students? The net electric field. But in the option, electric field is not there. Why? Because they are going to put a charge here. Now if you put a charge there, then the force is given by Q into E. If I take charge positive, if I take this charge, the test charge positive, then wherever electric field is there, there will be force, right? So for positive charge, force will be along this tangent. For negative charge, if I put minus charge, where will be force? This way, opposite to electric field. But electric field we always draw along the tangent to the field line. So force on negative charge will be opposite here. Okay. Now, they have not given force also in the option. They have given you velocity and acceleration. Acceleration is what from Newton's second law, force by mass. Since mass is just a scalar, it means direction of acceleration will be same as force. Understood? So, if I take positive test charge, force will be in the direction of electric field. So here your force will be in the same direction. And acceleration is always in the direction of force. So acceleration will be also in this direction. So which option matches with this solution? And what is the solution? Acceleration of the test charge will be along this tangent, provided the test charge is positive. So what is the answer? So this tangent gives you the direction of what, students? Acceleration. This tangent gives you the direction of acceleration for what kind of test charge if you keep here? Positive. So the right answer is option C. Imagine if you put negative test charge. Okay, so this is done. If you put negative test charge, then this will be minus because I am writing vector form. See, if you calculate magnitude, you can remove the minus, but we are talking about direction. So vector form you must mention with minus sign. So now this force will be opposite to electric field. So if force is opposite to electric field, and you know acceleration and force are in same direction, so in that case your force will be in this direction. So acceleration will be also in this direction. So now acceleration will not be along the tangent to the field line. Field line is this, no? So field lines will always have arrows. So wherever the field lines go, tangent should be drawn in that direction. Okay. So this tangent never gives you the velocity of the particle. It gives you the direction of electric field line. Some students know, they get confused. They think, oh, sir, in first PU we remember when you throw a ball at some velocity u, it goes in a curved path. And there if you draw tangent, that tangent gives you the velocity. Here why you are saying this tangent will not give velocity? Because this is path. P-A-T-H. Path means the points, if you collect the points where the particle is moving and you join those points, that is called path. This is not path, no, this is electric field lines. And the tangent to electric field lines does not give you velocity, it gives you electric field. So do not do the mistake of thinking that, oh, this is also path of projectile motion, so whatever tangent is here, that should be velocity, like that. So tangent gives you electric field, and for positive test charge, that tangent will also give you force. Now of course, if your charge is positive, and if it is at rest, if you keep the charge at rest, then wherever is force, there it will move. There will be acceleration, and see, velocity formula is what, students? U plus AT. Right now I am talking about vectors, so I am putting vector symbol everywhere. I am talking about direction. So now if initial velocity is not there, that means if you keep the charge at rest, then final velocity will be along the direction of acceleration. So in that case, velocity will also be here. So another option will also be right, but that was not mentioned whether the charge is kept here at rest or not rest. So if there is some initial velocity, then don't think your particle's velocity will be in the direction of acceleration. Understanding? So think again, see, Let us go back to your first PU concept. Acceleration due to gravity is down. Acceleration is down. Does it mean velocity will be down? Only if you keep the body at rest. See, then velocity is down. But if you throw the body like this, then its velocity after some time will be like this, tangent. So that velocity is not in the direction of acceleration due to gravity, which is always down. So remember, only if initial velocity is not there, then your final velocity and acceleration will be in same direction. But if there is initial velocity, then final velocity will be given by this vector plus this vector. So it will not be in the direction of this vector. Okay. So let us now see question number 9. So in question number 9, they are saying figure below shows the electric field lines around 3-point charges. So there are 3-point charges A, B and C. A is somewhere here, B is somewhere here, C is somewhere here. First you see the field lines. Okay, you will see lines are coming here like this. Here lines are going out like this. And here lines are going out like this. Okay, I'll not draw all the lines. So you have the question with you, right? So if you look at the question, it is very clear that this charge is positive because electric field lines are coming out. Here it is going in, so this is minus, and here it is coming out, so this is plus. They are asking in which region of this picture electric field could be zero. Electric field can be zero near A, near B, near C, they are asking. Now for this you go back to the picture which I made. Electric field lines for plus charge kept nearby. If you remember, it looked like this, right? And I told you why there is no electric field here, because at this point electric field is zero, because this will produce electric field away, this will produce away, and if they have same charge, then at the midpoint electric field will be zero. So between like charges, electric field can be zero between like charges. Now the question is, will it be in the midpoint? No, because if you look at the field lines, okay, you can see that more lines are here concentrated than here. Here they are quite far, right? Like this, they are quite like this. Here they are very much concentrated. Okay, like this is concentrated. So since lines are closer here, it means electric field here is stronger than here. That means this charge of C is greater than charge of A. But in this picture, if you remember, I told the charges are same. That's why at the midpoint electric field was zero. But here this has weaker charge. So near to that weaker charge, electric field will be zero. So answer is near A. Near A means option A itself. So whenever you have two like charges, then in between them electric field can be zero, and it will be zero at the midpoint provided the charges are same. We have done problems also, right? And if one charge is lesser than the other charge, then near the weaker charge electric field will be zero. Please revise the numerical section where we solve the problems. Okay, fine students. So try to remember that electric field lines are drawn to represent electric field. So they don't represent path of any particle. Only in one situation where electric field is uniform. Okay, like this, uniform electric field lines we draw like this, right? I told equidistant parallel lines. And now if you put here a positive charge that also at rest, then you know initially it is at rest means U is 0. So V will be where? AT. And A is what? Force by mass. And force in a uniform electric field is QE by M. Now since E is everywhere down, velocity will also be down. So the particle will follow this path. So the path will match with the electric field lines. Understood or not? The path of the charge will match with the electric field lines only in this case, when the charge is released from rest in a uniform electric field. But if you give this charge some velocity like this, u here, then it will follow parabolic path, right? Which we have seen already, because if you give velocity this side and force is this side, it will go in a parabola. Yes or no? We have discussed all these things, right? Okay. That two plates problem. Two plates was there and electric field was uniform and charge was coming this way. And when negative charge will come, it will go this way. And if positive charge will come, it will go this way. We have seen that problem, right? So the path of the particle will not match with the electric field line. Okay, unless the charge is at rest and the electric field is uniform. Okay, students. So now we can start solving transient material. Okay, before we start transient material, we can start transient material from next video. Anyways, almost time is up. So I will discuss some very interesting questions. Okay. So let me write this as extra questions again for entrance. Okay, hashtag. So suppose, look carefully. Okay. Suppose I give one charge Q here and one charge Q here, and I ask you where is electric field 0. Just now we have discussed, right? If the charges are equal, then at the midpoint electric field will be 0, because this charge will produce electric field here E1 and this will produce here E2, right? And since charges are same, electric fields also must be, in order to cancel, electric field should be same. So that this distance and this distance should be same. Then that means the point where electric field is 0 is at the midpoint. Everybody understood, right? Okay. So when charges are equal in magnitude, at the midpoint electric field is 0. Okay. Now let's say you have three charges in a equilateral triangle. And now I ask you what will be electric field at the centroid here. So here Q, here Q, here Q. So at the centroid here, what will be the electric field? Suppose I ask here. Answer is again 0 because of symmetry. But let me try to explain why it is 0. Okay. So due to this Q, electric field here will be away in this direction, right? E. And what will be the value of E? 1 by 4 pi epsilon naught. Source charge is Q. Distance between source charge and observation point, this is, let's say, R. Then R square. Now tell me what will be electric field here due to this. It will be same in magnitude, E only, because source charge is same as this, and this is R, means this is also R, right? This is also R. So same electric field will be this way due to this charge, and due to this charge electric field will be this way, and that will also have same magnitude. So you have three electric fields like this. This angle, this angle, this angle will be how much? Already we have discussed before, 120 degree. And if two vectors have same magnitude and they are at 120, resultant of these two, this and resultant of this electric field and this electric field will bisect this angle like this. So it will be E here, and that E and this E will be directly opposite, and they are equal also in magnitude. So total electric field will be 0. Understood all of you? So when two vectors of same magnitude are at 120 degree, resultant will also have same magnitude, and the direction will be bisecting this angle. And bisecting this angle means the resultant of this and this will be directly opposite to this electric field, the third electric field. So total electric field will be 0. Okay. So for two like charges, identical charges, at the midpoint electric field is 0. Similarly, for three charges in a triangle, at the midpoint of these three charges, midpoint of three charges in a triangle means where? Centroid. Their electric field is 0. Okay. Let us extend this concept now. So same thing if I ask you for a square, 2 we did, 2 charges, 3 charges. Now we will take 4 charges. So 4 charges symmetrically, how will you keep? In a square, right? Symmetrically. So now if I ask at the center of these 4 charges, means this intersection of the diagonals. So here if I ask what is electric field, answer is again 0. This is very easy to see. No need to do any vector addition, because for this charge it will be away, for this charge it will be away. And this Q and this Q are same, this distance and this distance are same. So electric field here due to this, and electric field here due to this will be equal in magnitude, opposite in direction. So they will cancel. Similarly, this charge will produce electric field here. This charge will produce electric field here. So total electric field will be 0. Net electric field will be 0 because they will cancel each other. Fourth one will be what shape? Can you tell me? It will be pentagon. Last time I struggled drawing the pentagon. You remember, right? So now I've learned it. Okay, it should be something like this. Something like this. Okay. So at the centroid of this, okay, here, if I put charge Q here, Q here, Q here, Q here, Q here, and I ask what will be the electric field at this point. At this point P, if I ask what is the electric field at P, then the answer is, from the logic which we are following till now, if you ask electric field at the centroid, it is 0. Okay. So like that again hexagon you can do. So point is, you have understood that if charges are symmetrically distributed, then at the center electric field will be 0 if equal charges are distributed symmetrically. Like charges are distributed symmetrically, then at the center electric field will be 0. So do not waste your time in exam finding electric field due to each charge and then doing vector addition. No point doing that, because answer will be 0. Now in NCRT example, there is a very good question based on this. So when you have 5 charges like this, okay, in a regular pentagon, this is your regular means it is symmetrical. This side is A, this side is A, this side is A, this side is A, this side is A. Okay, so in a regular pentagon, if you put like charges, identical charges in the corners, at the center electric field is 0. Now my question is, if one of the charge in the pentagon, which I have shown here, is removed, then what is electric field at center P? So if I remove this charge, let's say, okay, so if I mark this point A, if I remove charge from this A, now will it be 0? No, now it will not be 0, because there are more charges here and there is no charge here to balance the forces, to balance the electric field. We are talking about electric field, not force. So what will be electric field now? Can I say 0? Now it cannot be 0. So now the question is how much it will be. Now if you try to do it using vector addition, it will be very difficult, because first of all, now we see, if there was another charge Q and somebody will say what is electric field here, then from our knowledge of symmetry which we have done, 1, 2, 3, 4, we know electric field here is 0. Directly 0 we will tick if they put charges in the 5 corners. But question is, if this charge is removed, then what is electric field? Then it is not 0. Then how will you find? Due to this charge it will be away here, due to this charge away here, due to this charge away here, right? Due to this charge away here. So to find electric field for 4 vectors will be there, E. It will be very difficult, no? Because we have to add these two, then whatever answer comes, add with the third one, whatever answer comes, add with the fourth one. 4 electric fields will be there because of these 4 charges which we have to add. So doing this way will be very difficult. So I will teach you one fantastic trick, which is actually not a trick, it is a law, it's a principle. And that principle is called superposition principle. So look carefully again. So let me draw a regular pentagon. So this is not regular pentagon because this side looks longer, right? So somewhere here, let me go like this. Okay. So somewhere in the center. Okay, so this is A. So they want electric field here when charges are only here. Now let me think Suppose there was a charge here. Suppose, let us, I know they have not put charge, but suppose there is a charge here. Then the total electric field due to the five charges is equal to how much I have already told at center, at P. So at P, the total electric field here due to these five charges, if I put charge here, what is the answer? We have seen already, it is 0. But that is not the question. Question is to find due to these four charges. Now bring superposition principle. Okay, what it says? If you want electric field due to Pankaj sir, let's say there is charge on my body everywhere, then electric field due to this can be written as sum of electric field due to this plus electric field due to this. Where is my hand now? So electric field at any point due to this is basically sum of vector sum of electric field due to head plus electric field due to remaining part. That is the meaning of superposition principle, right? If I give you Q1, Q2 and I want electric field at a point, then the total electric field is vector sum of electric field due to Q1 plus electric field due to Q2. So knowing this, I can write electric field due to the five charges, which I know the answer already, 0 I know. This I can write electric field due to charge at A plus electric field due to four charges yes or no? So this is electric field due to the five charges. Okay, assuming I am putting a charge here, and if you put charge here, total electric field at point P due to the five charges is 0. Now from superposition principle you know that this electric field due to five charges, you can also write electric field due to this charge plus electric field due to remaining charge. Remaining charge is this. Now in the question they are asking this itself. Yes or no? So electric field due to four charges, four Qs, let me write four Qs, will be equal to minus of electric field due to 1Q at A. Like this. I am taking it this side. Now they want this in the question. And I have shown to you this is nothing but minus of this. And due to this Q, this part is very easy to calculate because this is electric field due to one charge only. Which point? And you know that each section here will be equilateral triangle. Okay, each section here, because this is a regular pentagon. So if this is A, this is also A, this is also A, all are A. So this distance is A, and the charge at A, which is point A, this is A, right? Okay. So the charge at A here, which I am assuming, this is the source charge. So this one I can easily write. So where shall I write? Is it space is there? Yes, space is there. Actually, much space is there. So this was the question, and this I am writing this as minus of this. So minus of, what is the formula? 1 by 4 pi epsilon naught q by this distance a square. And since it's a vector form, this is what kind of charge here? Positive. So it will be this way. So this here, if I write direction, if I write n cap, then this will be n cap. What if you write r cap? Whatever cap. Okay, r cap, and this will be r cap. Understood? So the answer for the question is electric field due to these four charges at P is minus of this. Matlab magnitude is how much? Magnitude of electric field due to these four charges will be magnitude if you take modulus. Magnitude is modulus. So if you take modulus, what is modulus of r cap? 1, because r cap is unit vector. So magnitude will be 1 by 4 pi epsilon naught q by a square. So that is the magnitude. Direction will be where? Direction will be minus r k. Remember, see, this is r k, but this is this vector is what they want. No, so this vector is minus r k. Minus r k means opposite to this. So it will be from P to A. Direction will be P to A if you remove charge from A. So this is how, by using superposition principle, I am able to do a very difficult problem also in a very simple way. So let me just quickly revise. How we did the problem. So we took a regular pentagon, right, and somewhere in the center. So here there was Q, there was Q, there was Q, there was Q, there was Q. I think before this point was made above, right? So it doesn't matter. Now, when you keep 5 charges, we know, all of us know, electric field here is 0. Total electric field is 0. But question was, one of the charges removed. Anyway, let us remove here. That means whatever electric, see, when there was charge here, whatever electric field this charge produces, which will be here, due to this charge, okay, let us write this A, that must be opposite to and equal to electric field due to these 4 charges. So this is electric field due to B, C, D, E. B, C, D, E. Then only electric field can be 0, right, students? So electric field here due to this charge is away from this point charge. And then I know, for due to these 4 charges, whatever each one of them is producing, I don't care. But remaining these 4 charges must produce electric field equal and opposite to this. Then only the total electric field here can be 0. That means now if I don't put this charge, this electric field will not be there. So this will be the answer. Understood? So electric field due to this 4 charge is equals to this, right? And this was how much? Minus of this electric field. And this electric field was due to only one charge here, right? So it will be 1 by 4 pi epsilon naught q by r square, and direction, this is the magnitude. Direction will be from center to that point where you have removed the charge. Okay, so keep this in your mind. So having understood this, next time suppose I give you another question. Suppose I give you a ring of charge, uniformly distributed. Okay, so lambda is dq by dl. Okay, now what is the electric field at the center? We know 0. Now suppose they say a small cut is done, a small cut, and suppose they say the length of this cut is dl. Then what will be the electric field now? Now can it be 0? No, because some small cut is there, right? So electric field of this part will not be cancelled, because here see, this part will produce electric field this way, this part. Similarly, this part will produce electric field ulta. So those two will cancel. So before, when there was charge everywhere, each part was cancelling the electric field of the other part. So total electric field was 0. But now if you cut, or if you remove a small charge from here, okay, then whatever will be the electric field due to this, that will be, as we have done here, that will be minus of, if you write vector symbol, minus of whatever electric field this charge was producing, this charge. And this charge will produce, since this is a very small cut, this is a what cut? Small cut. I can treat that charge which was present here as a point charge. So I can write 1 by 4 pi epsilon naught dq by this r square. Okay, and what is dq if they give lambda? Lambda into dl, right? Cross multiply. And direction, so minus sign means it will be opposite to the electric field produced by this charge. So this charge was producing electric field this way. this way, right? So remaining charge will produce that way. So electric field will be this way, direction will be this way. So since you want only magnitude and direction, magnitude we found from modulus, direction will be just like here, from center to the point where you remove the charge. Similarly, from center to that part where you remove the charge or where you cut. So electric field will be that way. Otherwise, finding electric field here due to this will be very, very complicated. Understood or not? So many charges are here, and then it is not circle also. It is circle. If you integrate, you will get 2 pi r, right? But here they have made a small cut. That's why the remaining part will look very complicated. However, the good news is whatever electric field this charge was producing here, this charge will produce opposite to that. So equal and opposite. So what I should simply do is find electric field due to the charge which was present here before. Opposite to that and equal to that will be the electric field of the remaining charge. Okay, so that is the beauty of superposition principle. See you next class with neat questions in our transcend material. Okay, thank you.